Welcome to the Deep Dive, your shortcut to understanding the fascinating world around us. Today, we're taking a truly mind-bending plunge into the parsimonious pursuit, Minimalism in AI Design by Gerardo Giovanni and Giovanni Giovanni, our mission. To uncover something pretty unexpected, how these ancient philosophical principles, from thinkers like Scotus and Ockham, how they aren't just dusty old ideas, but are actually profoundly shaping how we build and optimize artificial intelligence today. It's really about finding the surprising simplicity within incredibly complex systems.
Right. And for you, the listener, the core question we're really digging into is, in this cutting-edge world of AI, how can less truly be more? And this isn't just about, shrinking AI models for the sake of it. No, it's really about achieving optimal efficiency, deeper understanding, and maybe surprisingly even greater reliability. We're going to unpack the famous Occam's razor as well as our primary guide here.
Okay, so what does that mean for you listening? You're about to get a really unique perspective on AI design, connecting this deep philosophical wisdom with practical, real-world stuff. We'll try and focus on those aha moments, the unexpected facts, and the deeper why behind these design choices. Right, let's dive in. So let's start with Occam's razor. At its heart, it's this principle of parsimony. Essentially, the simplest explanation that adequately accounts for the data is usually the best one. Sounds straightforward, doesn't it? But think about this for a second. How could such a seemingly abstract philosophical idea be absolutely central to how we design sophisticated AI systems today?
Well, this applies very directly, pretty rigorously actually in AI. Occam's razor guides us to minimize model complexity. So if two AI models perform equally well, right, in explaining the data with similar accuracy, the one with the simpler, more elegant architecture is just, well, it's always preferred. And this isn't just about aesthetics, it means the AI is kind of forced to focus on the essential truths in the data, not just memorizing noise or random fluctuations. It often leads to models that are not just smaller, but also
More robust and maybe less prone to hallucinations because they're learning core patterns, not just superficial stuff.
Huh, that's fascinating. So it isn't just about saving space.
Exactly. Yeah, smarter is a good way to put it. We'll see it in techniques like pruning neural networks, where we literally cut away unnecessary neurons and connections. Crucially, without a noticeable impact on performance. Think of it like a sculptor, right? Chipping away excess stone to reveal the true form underneath. Another technique is quantization. This minimizes the precision of the data an AI uses. So instead of using highly detailed numbers, it might use simpler, less precise ones, which drastically reduces model size and computational cost. We also use things called regularization techniques like L1 and L2 regularization constraints. These basically put a tiny penalty on a model for being too complex. It subtly pushes it towards simpler, more general solutions, or Bayesian model comparison, which explicitly evaluates models based on both how well they fit the data and their complexity. It builds it right in.
Wow, okay. The practical benefits here sound huge for all of us using this stuff. It explains why AI developers often favor smaller neural networks and language models, like using small embeddings in natural language processing.
That's a great example.
Embeddings are like compact numerical fingerprints of words, right? That AI uses to understand meaning without needing massive dictionaries.
Precisely.
So it's about maximizing the benefits without unnecessarily increasing the cost. Simpler models mean minimal inference time. So faster results, which translates directly to minimal energy expense. You really see this when you think about AI running on your phone or maybe in a smart speaker or even out in the field on something like a drone. Edge computing and low-power devices where resources are just incredibly tight. Minimalism ensures these AI systems aren't unnecessarily wasteful. It's efficiency at its finest, really.
Now, as powerful as Occam's razor is, and it really is, there's a critical counterbalance we need to talk about. We should introduce Scotus's nuanced realism. This principle emphasizes the crucial interaction between the general, the broad abstractions, and the specific empirical details. In essence, Scotus encourages both the generalizability we absolutely strive for in AI, but also the absolute necessity to account for the unique, specific details we always find in real-world data.
Okay, so if Ockham is telling us to simplify, Scotus is kind of reminding us not to oversimplify, don't throw the baby out with the bathwater, to the point where you lose important nuances. It's like an AI learning the general roles of, recognizing a chair, that's the abstraction, but still being able to distinguish between, say, a sleek, modern armchair and a rustic wooden stool, picking up on those unique, particular details that make each one distinct. distinct.
Exactly.
And you're saying AI models actually embody this, for instance, in things like
Modular neural networks or maybe hybrid AI systems.
That's right.
These architectures that aim for a minimalist core, but one that can still intelligently zoom in on and handle the specific nuances of diverse data sets.
Precisely. Yeah, Scotus' principle helps clarify when adding more complexity is genuinely needed for, well, true understanding. It helps us account for the incredible variety and context inherent in real-world things, real-world entities. And this naturally raises a really important question for all of us working with, or frankly, impacted by AI. When is simplicity truly a virtue, and when does it, perhaps counterintuitively, become a hindrance to true understanding or accurate prediction?
Right, that's the big tension, isn't it? You see this debated in the research. I think Kim's paper mentioned this. There's this inherent challenge, an ongoing debate. Overly minimalist models, well,
It's a very fine line. Minimalism can actually be counterproductive. If that additional complexity would undeniably lead to significantly better accuracy, or maybe a more complete understanding, the key, really, is that AI systems have to be carefully calibrated. You implement minimalism only to the degree that adding more complexity doesn't provide a meaningful improvement. It's a delicate, ongoing negotiation between, let's say, elegance and effectiveness. Now, one clever way AI addresses
This balance is through what we sometimes call layered models. These models arrange entities hierarchically, sort of according to their representational capacity. You can think of it like biological entities, maybe.
Layers of neural networks extracting increasingly complex features, starting from low-level sensory inputs, like pixels in an image, maybe, all the way up to making sophisticated real-world predictions. So, what does this hierarchical layering mean for Occam's razor in a system like deep learning? I mean, deep learning seems to thrive on having lots of layers.
That's a fair question, but Occam's principle of parsimony still absolutely applies. Even there, you would still prefer fewer layers if those layers can be removed.
Without detrimentally reducing the model's accuracy or its overall efficacy. The ideal is always to have just enough layers to get the job done properly. No more, no less. And this
About blindly adding more layers, but really optimizing the ones you actually have.
Okay, so if we're constantly aiming for this delicate balance between simplicity and richness, where does this play out in the everyday AI we interact with? Like, thinking about your smartphone or your smart devices, let's maybe transition to a really practical application of computational minimalism, its use in context models, especially in those low-powered, resource-constrained systems like mobile devices and what they call context-aware computing. How do these systems manage to be minimalist yet still incredibly smart and responsive to their environment?
Well, they often achieve this using what are called polynomial time algorithms. For you listening, imagine algorithms that scale gracefully. That means the time they take to run doesn't just explode when the data gets really big, they stay efficient. These algorithms maintain sufficient context sensitivity while remaining computationally minimal. The trick often is filtering the incoming environmental cues, focusing only on those that are truly representative and filtering out the redundant ones. This is a direct, very practical application of Occam's razor. For instance, think about a sensor network. Individual sensors don't usually transmit all their raw data back. That would be too much. Instead, they collect it, maybe process it locally into summary statistics, and then they transmit only that filtered, condensed information upstream. This kind of data filtering mechanism ensures greater computational tractability. It just makes it much easier for the whole system to handle the load.
Right, and the immense benefit here is that these minimalist AI architectures can scale much more efficiently. Plus, they're also more likely to be decentralized, aren't they? Not relying on one huge central brain.
Exactly. Decentralization is often a key benefit.
It's a powerful approach, really, enabling AI to exist everywhere, not just in massive data centers. But of course, there's always a catch. A core challenge for these context-based systems is that they still have to adapt to the imperfect and noisy information of the real world.
Yeah, absolutely.
They can't just ignore the messiness. They have to deal with it somehow. Now, we've talked quite a bit about practical applications and these trade-offs, but what if the pursuit of minimalism goes even deeper? What if it suggests that the most profound understanding, whether for a human or an AI, inherently relies on simple, elegant models? Okay, here's where it gets really interesting, I think. Let's dive into another philosophical perspective, one that really challenges the assumption that more complex explanations are always superior. I'm talking about Langen's cognitive theoretic model of the universe, or the CTMU.
Ah, yes. Langen's CTMU. It definitely endorses a parsimonious model, one that carefully balances explanatory power with cognitive depth. It promotes something called a self-dual cognitive framework. For you, maybe think of it as a model that understands how the very act of knowing shapes what is known and vice versa, but without getting tangled in endless complexity. What this means, in practice, is that the CTMU aims to explain really complex relationships, like those between space and time, using a minimal set of underlying physics concepts. And crucially, it strives to retain both the explanatory and predictive efficacy of even the most complex, state-of-the-art theories of physics, all, supposedly, from a foundation of elegant simplicity.
Wow. So if I'm understanding this right, Langen is sort of suggesting that the most effective AI isn't one that just learns more data, but one that's designed from the ground up to recognize patterns and differences in the simplest, most elegant possible way. Almost like an AI that inherently understands the grammar of the universe itself.
Grammar of the universe is a nice way to put it.
That feels like a pretty radical shift from just, brute forcing solutions with bigger and bigger models. He even proposes AI should identify patterns and regularities through something he calls synephianesis, which sounds like a pattern comprehending unity of differences.
That's the term, yes. It's quite a concept. Langen certainly believes that simple, cogent models provide a higher quality of understanding and offer greater computational efficiency for AI systems. It's about building AI that doesn't just process data, but truly discerns deep, unifying patterns, even amidst this universe of specific, diverse data points. It definitely reiterates the need for ongoing critical evaluation and, well, recalibration of these models. We need to ensure they remain both efficient and effective in their understanding, whatever that means. So, okay, after exploring all these ideas, from Ockham to Scotus to Langen, we can probably reiterate that minimalism in AI design is a useful principle, a powerful one, but it's only truly advantageous when applied in certain circumstances. It's not a universal hammer for every nail, not broadly without reservation, which of course raises the important practical question. How do we know when to apply it? When is it the right tool?
Exactly. That's the million-dollar question, isn't it? To illustrate, maybe we'll have to go back briefly to that idea of a context threshold in context-aware computing. Remember, this describes how much environmental information the system needs to consider before it makes a decision. Now, if you set a higher threshold, it means the system needs more extensive environmental data, and it increases its sensitivity to changes. Which sounds good.
But there's a trade-off.
Right. Here's the trade-off. Higher thresholds can also degrade system performance because storing and maintaining all that information is very time and resource intensive. It costs more. On the flip side, a minimalist perspective seeks the absolute minimum number of nodes or variables necessary to account for the context. And this kind of minimalism brings other benefits too, like better latency, faster responses, and potentially enhanced privacy because less raw data is being processed or stored.
Yeah, and a pragmatic solution to address this constant tension, one that's gaining traction, is the use of hybrid cognitive architectures. These systems cleverly incorporate both symbolic components, think traditional rule-based AI, and connectionist components, like modern neural networks. Crucially, they can implement minimalism to varying degrees in different subsystems, or maybe under different environmental states. It allows for flexibility. It offers a more dynamic and hopefully intelligent approach to this whole tension. So to sum it up, in circumstances where computational expense is a critical issue, or perhaps where the benefits of increased accuracy and depth from adding complexity are limited, minimalism is clearly advantageous. Conversely, in systems where cost and latency are less of a concern, and where there's greater utility to be gained from increased precision or nuance, well, the benefits of minimalism may diminish. It's really all about finding the right balance for the right context.
And that, I think, brings our deep dive nicely to a close. We've explored this continuous dance, this tension between parsimony, that quest for elegant simplicity and representational richness, the need for comprehensive understanding in AI design. We've traced its roots from the, well, ancient insights of Ockham and Scotus all the way to today's cutting-edge computational models. It's clearly a tension that isn't going away anytime soon, and it continues to drive real innovation in the field.
Indeed it does. And it leaves us, and maybe you, with a final provocative thought to mull over. Given that these AI systems are constantly operating in incredibly complex, noisy, real-world environments, how might this ongoing pursuit of computational minimalism actually push us to fundamentally redefine what understanding even means for artificial intelligence itself? What stands out to you about this fascinating and sometimes tricky balance?
Lots to think about there. Thank you so much for joining us on this deep dive. We hope you continue to explore the fascinating intersections of philosophy and technology.